integration. Therefore, Bernoulli won't be that problematic. You understand? So now this is what is happening. I want to take you back a little bit so that you understand how to apply the Bernoulli. We have learned body separable, we have learned both homogeneous, we have learned both direct integration, we have learned both linear integration. So remember the standard form for linear ordinary differential equation, it looks like this. We say that dy over dx plus py is equals to q. This is the linear differential equation, right? So this equation, we say it is linear. Why? Because when you look at this equation, there is nowhere where we multiply with our independent variable. So meaning in this case, our independent variable, it is x. So meaning here, we are not multiplying by x. Even there, we are not multiplying by x. But here does not matter. Even if you multiply by x, it does not matter. But here, because you're not multiplying by x, so that means our equation, it is linear. So let me get rid of that x so that you can understand what am I talking about. So this standard form, it simply means that the equation, it is linear. But when we talk about the Bernoulli, it is not linear. Bernoulli, it is non-linear. You understand? So when you talk about the standard form for Bernoulli, it's gonna look like this. When we talk about the Bernoulli's ordinary differential equation, it's gonna look like this. It's when we have its standard form, dy over dx plus py. You see, it kind of looks like linear, but the problem is going to be this side, q multiplied by y to the power of n. So the moment our equation looks like this, it is no longer linear, it is non-linear. So here we have a non-linear differential equation. So in order for us to solve this type of equation, when we want to integrate, then we're going to have to use the Bernoulli's method. Okay, sharp, fine. So now, the standard form for Bernoulli, like I said, the standard form for Bernoulli, it is dy over dx plus py is equals to q multiplied by y to the power of n. And make sure that n may never be equals to 1. Because if n becomes 1, therefore this equation is going to be linear. But if n, it is any number that is greater than 1 or even less than 1, therefore our equation, it is non-linear. So to solve this non-linear, we use the Bernoulli, okay? And so we say n may never be equals to 1. The moment n equals to 1, we are no longer talking about the non-linear. We're talking about the linear. But in this case, it is non-linear, right? So when we apply the Bernoulli, there are two techniques that you can use, but there is only one of which I believe they assess us on, okay? Which is what I'm going to do with you right now. So on how to solve the equation. But what I'm going to do here is I'm going to give you on how to go about to solve the Bernoulli. Look, so what's happening over here is you are given the non-linear. So you know what we're going to do with this equation? We're going to make it linear, meaning we want to linearize this equation. But the question is, how are we going to make this linear? We're going to make it linear so that it looks like this, maybe dy over dx plus py is equals to q. So meaning we're going to get rid of y to the power of n. So the first thing that we're going to do is let's divide both sides by y to the power of n. So when we divide both sides by y to the power of n, divide by y to the power of n on that side, mean we're going to have something that looks like this. On this side of the equation, we're going to have 1 y to the power of n dy over dx plus even this term over here, we're going to have 1 over y to the power of n multiplied by p. And on this side of the equation, we're going to left with q, right? This is how now our equation would actually look like. Now, at this point in time, we are still not looking at the linear equation. Why? Because look at this over here. It is only if we had 1 over here, just like that means we're going to have to get rid of this. But the question is, how are we then going to get rid of this? Now, this one is going to take us a long step so that we can have equation that looks like this, where we can apply linear equation. You understand? So here we are reducing it first. So the second step is we're going to let...
La py. Actually, we divided by y to the power n. Well, and
Oh, here we have
then
y, yes. Oh, minus 1 here. It's going to be minus 1.
minus 1.
You get it, y?
Yeah.
Okay, because p over y divided by y to the power of n. Remember, laws of exponents. We have p y to the power of, do you see this n here? It is at the bottom, but when we take this one at the bottom, it's going to be negative 1. And that's why we have negative 1 there. Okay, yeah, I think I forgot that negative 1 over there. And therefore, now what we're going to do after the following this step, after this step, we're going to let you can pick any variable and pick z, you can, but let's let u. So we're going to let u to be equals to the coefficient of p, okay? So meaning we're going to have 1 divided by y to the power of n subtract 1. And therefore, from here, from here now, what we're going to do is we're going to differentiate this equation that we have just formed over here. So when we derive this side, we're going to have du over our independent variable in this case, which is dx, is equals to this side. We're going to do the same thing. But before I can do that, you know what I want to do? So that you don't get confused. This thing, we can rewrite it like this. This thing, we can rewrite it like this as y, so that we can differentiate. This thing, we can rewrite it like this. Y to the power of, when this exponent goes at the top, 1 is going to be positive, and n, it's now going to be negative. So meaning u is equals to that. I just rewrote this equation. So now when I differentiate this side, I'm going to have du over dx. When I differentiate this one, remember, we're going to take the exponent 1 minus n multiply by y to the power of, and then there on the exponent, what are we going to do? We're going to minus 1. So we're going to left with negative n over there. But if you have a look at this, we just differentiated u in respect to x, but our variable over there is y. So for the fact that this is y, then we're going to have dy over dx on this side of the equation. Remember, from here to this step, what did I do? Firstly, I divided by y to the power of n, and then I got to this step over here. And then from here, I'm going to take the coefficient of p, I'm going to equate it to u, or you can even equate it to z, whatever variable that we want to pick. And therefore, from this equation, I'm going to differentiate so that I move to this step, meaning I differentiate this side. But be careful, this side we are differentiating in respect to x, and we don't have x this side. You see, there is nowhere where we have x. So hence why after differentiating this variable, which is y over here, we're going to write dy over dx. And okay, and then from there, remember our aim is to make sure that we get rid of this, right? So now what we're going to do here from here is that from this equation, I'm going to manipulate this equation so that it looks like this thing that I see over here. You see, we have dy over dx. I have dy over dx. Can you see that? I have 1 over y to the power of n. So that means I'm going to have to manipulate this equation to look exactly like that. So what I'm going to do is I'm going to divide both sides by 1 minus n, which is this. And then this side, I'm going to have 1 over 1 minus n, close the bracket, du over dx. And therefore, this is going to fall off. Remember, this thing, it is the same as 1 over y to the power of n. And I'm going to left with dy over dx. Now I can see that this side of the equation, it is now the same as that side of the equation. You understand? And therefore, from there, what I'm going to do is I'm going to substitute this thing over here to there. Right? Meaning where I see this, now I'm going to write this part of the equation. So I'm going to substitute the whole expression on this side of the equation over here. Over here. Meaning I'm going to write this thing. Therefore, we're going to have 1 over 1 minus n du over dx. And if I continue with my equation, here I have plus, remember? So I have what, plus this. I have plus that, right? And therefore now, this is what is happening. Once more again, remember, we just said this thing over here is equals to u. So that means here we're going to have u multiplied by p is equals to, and then on this side of the equation, we're going to have our u. And therefore, now I'm going to get rid of this. I'm going to multiply both sides by 1 minus n. So when I multiply by 1 minus n, I'm going to have dy over dx. Plus here, I'm going to multiply by y minus n. I'm going to have u multiplied by p. Even this side, I'm going to multiply by 1 minus n multiply by q. So now if you look at this equation, now this equation, it is linear. From here, we can apply the linear differential equation to solve for our equation. So that means this equation now look like dy over dx plus, I want to write this p, which is this p over here. This is my p, and then my y will be the same as 1 minus n multiplied by u is equals to q 1 minus n. Now this equation, it is linearized. Therefore, from here, what I can do is I know that from here I can apply my linear ordinary differential equation method or technique to solve this equation. Do you understand? Wait, let's start here. Do you understand how I went about from where I started to here?
Yes, I do.
You are sure 100% you understand?
Yeah.
Okay. So now if you understand, now let's solve a question. If you understand.
Okay.
Now here's the question, right? We're gonna apply, you see the same thing that I did over there, we're gonna do it over here.
All
right, so now here what's happening is we are given the equation. Remember, in exam, they're not gonna tell you which technique to apply. You should be able to see by yourself. Is the parallel gonna work, homogeneous or whatever? You're gonna have to be able to check it for yourself. So now in this case, let's talk about this equation. Does this equation to you? Let's see. Remember, the standard form for linear, it's supposed to be dy over dx plus py is equals to q. So if I try to make this, make sure that here is y and that's y. You see, those are the dependent variables, supposed to be the same. So let's see if we have something like that. So we have dy here over dx plus, okay, we have xy is equals to xy squared. Now, having a look at this side over here, we're not supposed to have y. The moment we have y to the power of n, just like this thing over here, this is y to the power of n. I don't care about x. I don't care about x. It's fine. This part over here, it's linear. But the problem, y to the power of 2 will make this equation to be non-linear. So then if this equation, it is non-linear, then I'm going to apply the Bernoulli. You understand? So you have to check it yourself before you can solve it, because they're not going to say apply Bernoulli. You should be able to know I'm going to apply the Bernoulli. So that means this equation, it is non-linear, right? Fine. So what are we going to do? We're going to make it linear, just like how I showed you. So meaning we're going to say dy again over dx plus xy is equals to xy to the power of 2. Remember, we're going to divide both sides of the equation by y to the power of 2, right? So meaning if I divide the whole equation, I'm going to have 1 over this, and then dy over dx. And then this side, when I divide both sides by y to the power of 2, I'm going to have x over y. Do you agree with me? Okay, yes, let me write it like this. Now it's fine. I'm gonna have x over y, because I'm gonna divide by y to the power of 2. And then this side, I'm gonna divide by the whole thing. Therefore, I'm gonna have x. Now, what is the second step? You're gonna let, just like how I showed you after the step. What are we going to let? The coefficient. Remember, we said we let the coefficient, which is this. If you still do remember from the basic, we said we let u to be equals to the coefficient of this p over there, meaning we let this thing that has y. So meaning in this case, let, that's why I wanted to write it like this. Let me rewrite it. It's not wrong there, just that I want you to see it. So y over 1, and then let me say multiply by x, ne? just want to write it like this. So meaning in this case, our P will serve as X. So meaning we're going to let our U to be equals to 1 over Y. So meaning we're going to let U to be equals to 1 over Y. Now here's another hint. The variable that you're going to let to be what? Look at here. Here we have squared, and then there we have to the power of 1. So eventually at some point, working with this equation is supposed to take you there. Okay, so but it's fine. Just however you want to look at it, it is still fine. So meaning we're going to let U to be equals to 1 over Y. And remember, this is Y to the power of negative 1. And then we're going to differentiate this equation. We're going to say du over in respect to the independent variable dx. And be careful, sometimes could be dx over dy. So you should be able, it's not always the case like this. Please, sometimes the question that I sent in the group, the first question that I sent, you apply linear there. And you're supposed to understand that it will always not be the case to have your variables like this. Sometimes they can be like this, dx over dy. So meaning this is the dependent. So that means it's supposed to be x and then q. dz over dk, meaning it's going to be p z is equals to q. So you should be able to understand these things, because sometimes your independent and dependent variable can change. So that's why here I'm also emphasizing, because you never know how the question is going to be presented to you. So, but the thing is, here we can see it, and those are the silly mistakes of which you can forfeit your marks. So dy over dx, meaning du over dx, there is no x in this equation, but I'm going to derive in respect to x. If here was t, I'm going to say du over dt. Okay. Du over dx, and then let's derive this, let's differentiate this side. When you differentiate this side, remember, take the exponent there, it's going to be negative 1, and then we don't need to write that negative 1. Negative 1, you're going to get negative 2. This is differentiation. But because we are deriving in respect, we are deriving y, so that means you're going to have dy over dx. And therefore from here, remember, you're going to manipulate this so that it looks like this side of the equation. So meaning we have du this side over dx. So what I'm going to do is I'm going to divide both sides by negative. So it comes negative this side, and then here I'm going to have positive. But remember, this is the same as 1 over y to the power of 2 dy over dx. Now this looks exactly the same as that. Now I'm going to write this thing in that position. So meaning I have negative du over dx, and then this is it. I substituted that, and then plus that. Remember, we said u is the same as 1 over y. We said u is the same as 1 over y. So meaning here I'm going to write u x is equals to this side of the equation. I have my x. Right? So now, what am I now going to do? I don't want negative here. I'm going to get rid of this negative. Remember, I need to make sure that they have a positive one all the times. So meaning I'm going to have du over dx. Therefore, this will be affected. It will be negative u x is equals to x. Now, what do we see? Do we see a linear equation, or do we see a non-linear equation? Now, this is a linear equation. Oh, it's going to be negative because I divided.
Let me check.
So now we have a non-linear. Come again.
Can I please check the part where we are substituting?
Okay, yeah, exactly. I agree this is the equation, so I didn't want to confuse you that side, because from here it's linear. You see, the linear, the one that you know, this is the linear now. So meaning, let's talk. When we want to determine the linear, we have to determine the integration factor, right? Meaning we have to know what is the value of P, we have to know what is the value of Q from this step. So at this point in time, our P is going to be what? Remember, linear says dy over dx plus py is equals to q. So this is the variable, this is the variable here, this is the variable, this is the variable. So that means our p is going to be negative x. You see? And then our q is going to be that negative x as well. So why am I saying p is negative x, not positive x, because this thing again, you can rewrite it like this, okay? You can write positive there, and then so that it gets to the standard form, and then negative x there, and then we have u there is equals to negative x. So now let us determine the integration factor. The integration factor, which is denoted by r, is equals to e to the power of integral of, remember, we substitute p there, which is, let me take my negative this side, dx. And therefore, what is the integral of x? The integral of x is going to be what? E to the power of what? It's going to be e to the power of negative x squared divided by 2. This is the r. Now, let us solve this equation. We're going to say r multiply dependent variable, it is y, is equals to the integral of q multiplied by r d independent is dx. And therefore, let's substitute. What is r? We said r, it is e to the power of negative x squared divided by 2, close the bracket, multiply by y, is equals to the integral of, in this case, our q is equals to how much? Let me take negative outside, it's x. So meaning we have x multiplied by r, which is e to the power of negative x squared divided by 2 dx. And from here, how we're going to integrate this? We are multiplying two equations, right? So at this point in time, it's a matter of now your integration skill must be at you must be good at your integrating. You must know how to integrate. So here I can use U substitution. I can use U substitution. Was I gonna be able to use by parts? Let me see if I wanted to use by parts. Let me use U substitution. So if I use my U substitution, what am I going to do? I'm gonna say I'm gonna let, okay, already, because I'm dealing with you, I have already dealt with you, but yeah, it's only this part is fine, so you don't have to worry. So in this case, I'm gonna let my u, v or u, whatever, u, to be equals to the exponent over there, which is negative x squared over 2. And then from here, I'm gonna differentiate this du over dx. So what is the differentiation of this thing? You take 2 there, multiply is gonna give us negative x dx, right? And then remember, this equation can be written as negative 1 over x du is equals to dx. So that in the position of dx and the position of dx, I can write this thing over here. Then x will cancel that x, and negative will cancel with that negative. And then, yeah. So let's go. So here, we still have this part, but let me just continue this side. So that means I'm going to have the integral of x will cancel x, and then I'm going to have du and this part. And remember, this part is u. So I'm going to have e to the power of u du. And then what is the integral of e to the power of u? The integral of e to the power of u is going to be e to the power of u. Why am I writing du now? It's going to be e plus c, because this is the indefinite integral, plus c over there. And then remember, this side we have e to the power of negative x squared divided by 2 multiplied by 1. And therefore this will be, oh, remember we said u is equals to how much? We said u is equals to, back substitution, let's not forget that we are not so, we said u is equals to, what is it? It's negative x squared divided by 2, and then this is the final answer. This is the final answer implicitly. But when they say represent your final answer explicitly, then you're going to have to make y subject of the formula. Meaning explicitly, we're going to say y is equals to, we divide by this thing. Here we're going to have 1, it's going to cancel. Then plus c, e to the power of, it's going to be positive now, x squared divided by 2. This is explicitly. Yeah, so you see all of the Bernoulli equations, you do the same thing over and over again. This is the only thing that you need. You need the basic and one question. And every question, you can even give me a question. I'm going to do it like this.
Young stress. Okay, I'll try questions and then we'll see.
Okay.
Yeah.
Okay.
Hey, Siama, Maths. Hey,
Yeah.
it's a lot, Ndoda.
No,